Here we are on part 3, page 8 again, and we're taking a look down a stream on this page here at homeostasis. Homeostasis is a steady state input and output of the human body. We begin as a live cell when a sperm fertilizes an ova or an egg. Several days later, the egg hatches and implants into the uterus and becomes an embryo. The embryo, after 2 months, becomes a fetus. A fetus grows up under the influence of oncogenes for rapid growth, and we become born as a neonate newborn at the end of approximately 9 months or so. So that's some pretty quick work to make trillions of cells. So homeostasis is a steady state. Once there is a heartbeat in the fetus, the heartbeat will last until the very last day of life. If it's 115 years old, that's how many years the heartbeat will go. And there will be no equilibrium. This discussion here that homeostasis is something that has to do with a dynamic state of equilibrium is wrong. By definition, equilibrium is a system at rest, chemically at rest, with complete uniformity, and there are no diffusion gradients in an equilibrium system. Therefore, biology is basically making a significant error. When I was in medical school on the very first day of biochemistry, Dr. Richard Ludueña, our professor at the University of Texas, said, equilibrium is death. And it is important to understand homeostasis in that light from this day forward, if you would please, that there is no equilibrium. Equilibrium is a state in which a system is homogeneous throughout, that is to say, that it is a system at rest in which all of the forces have balanced with each other, and now there are no, how shall I say, forces that are involved in movement or diffusion gradients of any kind. If there are multiple diffusion gradients, then they are at balance, and it's over, it's finished. There's no input, there's no output. It's a system at rest, and that, by definition, is death. So, at all costs, avoid the word equilibrium. It's an unfortunate thing that biologists do have a tendency to use this word from time to time when they really mean to say balance. That's what they really would like to say. They say, oh, or balance. Do you see that right there? Okay, I'm bringing out a little partisan politics here, chemistry versus biology, but it's an important issue that you might want to embrace at some point in your life because balance is really different from equilibrium, especially in an ongoing system in which there's ongoing synchronicity, there's ongoing flow-through, and the steady state brings about a steady amount of a certain concentration of things, and that would be the balance aspect, right? You'd like to be continuing to have oxygen at a certain level throughout your body, and you have to breathe in and breathe out in order to make that happen. In order for nutrients to travel through, you have to both eat and you have to defecate and urinate in order for that to happen. There has to be an input, an output, and a flow-through. Okay, so in fact, the word pain is an indication that things have stopped flowing through. And so stasis, by definition, is often associated as a common definition of pain. You'll see that in inflammatory systems. So I need to be strong about this. Equilibrium is death, and homeostasis is life. I want you to be well aware of that. Okay, so we have a steady state system. There are a couple different pathways for this to happen. One simple pathway, I'll have this as a handout, and I'll make it available to you. So one way is the biosynthetic pathway. Whenever we start with substrates, we start with the things that we need to put together in order to get a product. In a car factory, you begin with parts, and the parts are assembled, and then you get a product. Sometimes it takes multiple stages of assembly. As long as you have the parts and all the machines in the system are on, then basically the parts themselves mean let's turn the machine on. So substrates actually increase the K rate, or rate of reaction of enzymes. Once the products are present, that's going to actually reduce the K rate, it's called, of the enzymatic activity. Enzymes can run fast or slow. Okay, so once we have substrates, we get an increase in speed, sometimes many orders of magnitude, sometimes 1,000 or 1,000,000 times as fast. And once we have products, we can slow down that enzyme. Now, on the other hand, if these happen to be the substrates of the next enzyme in the pathway, then they'll be taken up. They will have stimulated the enzyme in its K rate, and you'll be adding new things at that point, and we'll have yet a further developed product. And that will, in fact, turn off the enzyme, or it could get removed and moved to the location where that product is needed, either as a structural product or as a worker molecule, like a hormone, or an enzyme itself is made this way. This could be producing an enzyme. Okay, so this is the biosynthetic pathway, in which the substrate turns on the enzyme, the product turns off the enzyme. We have to move it on. That's why we have not only synchronicity, not only is there balance, the right amount, there's also uninhibited flow-through, right? We have to bring the substrates and we have to remove the products, right? If somebody has constipation, they're in big trouble, right? We have to have flow-through. Okay. Here we have a brain. I like to say it's Lyle Alzado's brain, and I'm using his name here not to disparage him, but because he was one of the first people to admit to something long ago, I think, and just long ago. He was on the cover of Sports Illustrated, and a very sad face. Lyle had as a subscript to his name, "I lied." What do you think he lied about? He lied about, it turns out, the use of steroids. So I'm looking at negative feedback homeostasis here, and I'll bring the syringe into it at the end. So here we have the brain up here. We have the hypothalamus and the pituitary. The anterior pituitary makes lots of interesting hormones, including growth hormone, but in this case we're going to be selecting just these two right here. Luteinizing hormone and follicle-stimulating hormone are released regularly from the brain, right up here. It's a constitutive output. Constitutive meaning on all the time until we turn it off. A lot of negative feedback works this way. This is on, okay, and then it's going to stay on until something happens. And whatever that something is, we'll turn it off. Okay, if you need heat in your building, the furnace will stay on until the temperature gets up. If you need cooling, the air conditioning will stay on until you get to a certain point, and then it will go off. Okay, it's not on always every second. So here we have a gonad down here. It could be a testis or it could be an ovary. And LH is going to make certain hormones happen. In the male, it will make testosterone happen. In the female, we'll be working with 2 molecules instead of 1. It'll be estrogen and progesterone. You could say progesterone is the more macho version, and estrogen is the more feminine version, and the testosterone sort of resides somewhere between those two, and males try to do it all with 1 molecule right here, but females get to have 2. And the deal is that they feed back. Notice that I have plus signs right here. Notice that on the feedback loop, I used a dotted line, and I'm getting negative signs, which means I'm turning off the system. It's once you get enough of these hormones at the adequate concentration in the blood that you need, that concentration will be adequate to turn off the system at the highest level, and we will stop producing LH and FSH or reduce it greatly, and then we'll be in a steady state, balanced homeostasis, just the way you like it. Okay, so then we'll consider interruption in our next segment here, which is number 4.